Hello and welcome back to G Fun Facts Online. Today we are diving deep into a topic that sits right at the intersection of biology, robotics, and the human experience. We are talking about the sensory renaissance in bionics. Specifically, we are going to explore how engineers are finally giving prosthetic limbs the one thing they have always lacked: a sense of touch. Let's start by grounding this in something we all understand. Think about the sensation of wind on your face, the warmth of a morning coffee mug, or the reassuring grip of a loved one's hand. These aren't just physical events. They are sensations that define what it means to be human. But for millions of individuals living with limb loss, the world has traditionally ended exactly where their prosthetic begins. For decades, prosthetic limbs have been absolute marvels of mechanical engineering. They are sophisticated, articulated, and strong. But they have also been failures of sensory integration. To the user, these advanced tools are dead to the world they touch. A user could crush a paper cup or drop a fragile egg simply because they cannot feel when they have made contact. But this disconnect is now ending. Through the convergence of soft robotics, neural engineering, AI, and material science, we are witnessing the dawn of a new era. Today, we are going to trace the journey from wooden pegs to cybernetic limbs that can feel, heal, and communicate directly with the human brain. To understand the gravity of this technology, we first have to understand the deficit it seeks to cure. I want you to imagine driving a high-performance sports car. It has a powerful engine, precision steering, and perfect aerodynamics. Now imagine driving that car with a completely numb body. You cannot feel the vibration of the road through the seat, you cannot feel the resistance of the steering wheel, and you cannot feel the pedal under your foot. You would have to stare at your feet just to know if you were braking. You would have to watch the steering wheel intensely to ensure you weren't drifting. This is the daily reality for a traditional prosthetic user. It is a problem known as open-loop control. In a biological limb, the system is a closed loop. The brain sends a motor command, like close hand. The muscles execute it, and the nerves in the skin immediately send feedback, saying hand is closing or object contacted. The brain adjusts the grip force milliseconds after contact, largely subconsciously. In a traditional prosthetic, the brain sends the command via electromyography sensors on the residual limb, and the hand closes. But no signal comes back. The loop is open. The user must rely entirely on visual feedback. They have to watch the hand to see if it has grasped the object. This imposes a massive cognitive load. The user cannot multitask. They cannot grab a water bottle while watching TV. The prosthetic requires their undivided attention, making it mentally exhausting to use. This sensory void leads to a phenomenon known as device abandonment. Studies have shown that up to 30% of upper limb amputees eventually stop using their expensive myoelectric prosthetics, reverting to simpler body-powered hooks or no prosthesis at all. Why? Because a simple hook, connected via a cable and harness, offers what is called mechanotactile feedback. The user feels the tension of the cable on their shoulders. A $50,000 bionic hand, despite its robotic beauty, often feels like a foreign object, a heavy, numb tool hanging off the body. Haptic feedback is the key to closing that loop. It is the bridge that turns a tool into a limb. So how do we build an artificial sense of touch? Engineers have had to reverse engineer one of nature's most complex systems, the human skin. Skin is not merely a wrapping. It is a sprawling, intelligent data collection surface. The challenge is that touch is not a single sensation. It is a symphony of inputs processed by specialized biological sensors called mechanoreceptors. A truly realistic bionic limb must replicate the functions of at least 4 distinct types. First, we have Merkel discs, or slow-adapting type 1 receptors. These are responsible for sensing sustained pressure and texture. When you hold a pin, Merkel discs tell your brain that the object is still there. They provide the image of touch. Second, we have Meissner corpuscles, or fast-adapting type 1 receptors. These are tuned to low-frequency vibrations and light touch. They are crucial for grip control, detecting the microscopic slip that happens just before you drop an object. Third, there are Ruffini endings, or slow-adapting type 2 receptors. These detect skin stretch and joint position, known as proprioception. They tell you the shape of your hand even when your eyes are closed. And fourth, we have Pacinian corpuscles, deeply embedded in the dermis. These detect high-frequency vibrations, allowing you to feel the hum of a running engine or the texture of a rough wall through a tool you are holding. Early attempts at prosthetic feedback were crude because they treated touch as a binary signal, contact or no contact. Modern haptic systems are biomimetic. They attempt to encode data into electrical signals that mimic the specific firing patterns of these biological receptors. The goal is to trick the brain into believing the signals are coming from a biological hand, not a silicon chip. The most immediate and commercially viable solutions for sensory feedback are non-invasive. These systems do not require surgery. They sit on the surface of the residual limb, often called the stump, and translate data from the bionic hand into sensations the skin can feel. The most common form is vibrotactile feedback. similar to the vibration motor in a smartphone. Sensors in the prosthetic fingertips detect pressure. When the pressure increases, a small actuator on the user's residual limb vibrates. However, there is a mapping problem here. A vibration on the forearm doesn't naturally feel like a touch on the finger. This is a sensory substitution. The brain must learn that a buzz on the forearm equals pressure on the index finger. Modern systems use somatotopic mapping to place an array of vibrators in specific patterns, so users can distinguish which finger is touching an object. Advanced tactors can even vary frequency and amplitude to simulate texture. A high-frequency buzz might mimic glass, while a low, rumbling throb mimics sandpaper. Another method is electrotactile stimulation. Instead of vibration, this method uses small electrodes on the skin to deliver a mild, painless electrical current. These systems offer higher resolution than vibration. A small electrode array can transmit more detailed information, like the shape of an object. The challenge here is the paresthesia challenge. The sensation is often described as a tingle, or pins and needles, which some users find unnatural. But by modulating the pulse width and frequency, researchers can create sensations that feel more like pressure or tapping. Then we have mechanotactile, or force feedback. This is perhaps the most intuitive method. When the prosthetic hand grips an object, a motorized pusher presses into the soft tissue of the user's residual limb. Unlike vibration, which is abstract, pressure feels like pressure. This system helps significantly with grip force modulation. If the user squeezes a cup too hard, the pusher presses harder into their arm, warning them to back off. Newer devices even use rockers to stretch the skin of the forearm, simulating the sensation of the fingers bending to restore proprioception. Perhaps the most fascinating advancement in non-invasive tech occurred in 2023 and 2024 with thermal feedback. By using Peltier elements on the residual limb, prosthetics can now transmit temperature. This has functional safety benefits, like knowing if a coffee is too hot, but the emotional impact is even greater. In trials, users reported that holding a loved one's hand felt significantly more emotional and real when they could feel the body heat. This affective touch is crucial for psychological embodiment. While non-invasive methods are safer, they are limited by the bandwidth of the skin on the residual limb. To achieve true high-fidelity touch, scientists are bypassing the skin and going directly to the source, the nerves. This is the invasive revolution. One approach is peripheral nerve stimulation, or PNS. Surgeons implant cuff electrodes or microelectrode arrays, like the Utah slanted electrode array, directly into the median, ulnar, and radial nerves of the residual arm. When the prosthetic sensors detect touch, the computer stimulates the specific nerve fibers that used to connect to the fingers. The result is profound. The user does not feel a vibration on their stump. They feel a sensation on their missing thumb. This is called referential sensation. By using algorithms that mimic the firing spikes of natural mechanoreceptors, known as neuromorphic encoding, researchers have enabled users to distinguish between hard and soft objects, and even textures like corduroy versus cotton. Another surgical technique is targeted sensory reinnervation, or TSR. This procedure rewires the body to create a biological display. Surgeons take the sensory nerves that once went to the hand and surgically connect them to a patch of skin on the chest or upper arm. Over several months, the nerves grow into that patch of skin. When you touch that spot on the chest, the patient feels it as if you are touching their missing hand. Engineers then place tactor arrays on this reinnervated skin map. When the prosthetic touches an object, the tactor pushes on the chest skin, and the brain perceives it as a touch on the phantom finger. This provides a completely naturalistic, non-invasive interface for an invasive surgical result. We also have osseointegration and osseoperception. Osseointegration involves anchoring the prosthetic directly to the bone using a titanium implant, eliminating the need for a socket. Because the prosthetic is fused to the skeleton, vibrations travel through the device and into the user's bone. Users report a heightened sense of the environment, mediated by the body's natural vibration conduction. They can feel the texture of the floor through a prosthetic leg, or the crunch of an object in a prosthetic hand. The hardware on the prosthetic itself is also undergoing a revolution with electronic skin, or e-skin. Rigid force sensors are being replaced by flexible, stretchable, sensor-laden materials. Researchers at Stanford University developed a soft integrated circuit that acts like a nervous system. This e-skin can sense pressure, strain, and temperature simultaneously. It processes data locally on the limb, mimicking the peripheral nervous system's ability to filter noise, and the polymers used can even self-heal if torn. Similarly, ACEEES, or asynchronous coded electronic skin, developed at the National University of Singapore, functions like a nervous system on a chip. It detects touch 1,000 times faster than the human sensory system and uses a single wire to transmit data from thousands of sensors, making it robust against damage. These skins are moving us toward distributed sensing, providing total spatial awareness rather than just fingertip sensation. The benefits of these technologies extend far beyond dexterity. They reach into the psyche. One of the most significant impacts is on phantom limb pain. This is a debilitating condition where the brain, starving for input from the missing limb, generates pain signals due to a cortical reorganization error. Haptic feedback provides the brain with the input it craves. By restoring the flow of information, the brain calms down. Studies involving peripheral nerve stimulation have shown dramatic, long-term reductions in phantom limb pain. Furthermore, haptic feedback restores the sense of embodiment. This is the feeling that the prosthetic is part of you, not just attached to you. When visual feedback matches sensory feedback with less than 100 milliseconds of latency, the brain accepts the device. Users report a higher sense of agency and ownership, leading to better care of the device and more confident social interactions. Let's look at some case studies to see this in action. In a landmark study, a user equipped with a sensory feedback hand was tasked with the cherry stem test. They had to pluck the stem off a cherry while blindfolded. Without feedback, the user either crushed the cherry or failed to grip the stem. With haptic feedback, they could feel the delicate compliance of the fruit and the resistance of the stem, successfully completing the task. Then there is the box and blocks test, which measures manual dexterity. Users with haptic feedback consistently move more blocks per minute, approaching the speed of able-bodied individuals, because they can grab without hesitation. But perhaps the most moving testimonial comes from Kevin Walgamot, a participant in a University of Utah study using the Luke arm. When he first held his wife's hand with the sensory-enabled prosthetic, he wept. He said it felt like he was holding her hand. He could feel her fingers interlaced with his robotic ones. This highlights that the ultimate goal of bionics is not just function, but connection. Despite the miracles occurring in labs, hurdles remain. Surgical stability is a major challenge. The body attacks foreign objects, creating scar tissue that insulates electrodes. Developing biocompatible interfaces is the holy grail. Power consumption is another issue. Processing complex haptic data taxes batteries that are already running motors. Neuromorphic chips are being developed to solve this. Then there is cost. A bionic hand can cost up to $100,000, and adding haptics pushes this further. Democratizing this technology through 3D printing and open-source software is critical. Finally, we still face the challenge of signal complexity. We need better algorithms to translate digital sensor data into the nuanced, fluid language of neural spikes. In conclusion, we are standing at the threshold of a new era in human evolution. The distinction between biological and artificial is blurring. Haptic feedback systems are not just accessories, they are the wiring of a new nervous system. In the near future, we will see bionic integration, where amputation is an alteration of interface rather than a disability. We will see AI-driven prosthetics and electronic skins that offer superhuman sensitivity. The journey of the amputee has effectively shifted from rehabilitation to augmentation. By closing the loop, and by giving the machine the power to feel, we are finally returning the lost sense of wholeness to the human body. The prosthetic of the future will not just be a hand that moves, it will be a hand that holds, feels, and loves. Thanks for tuning in to G Fun Facts Online.